All right, today we're going to dive into one of nature's most fundamental forces, one that's, quietly powering pretty much our entire modern world: magnetism. Well, the answer, of course, is magnetism. It's this invisible force that connects all three: the electric motor in your car, the way data is stored on your computer, and even that simple little needle on a compass. So, to really get how magnets basically run our world, we got to start with the basics, right? What exactly is a magnet? Okay, so at its core, a magnet is something that creates this invisible field of energy around itself, a magnetic field. And inside that field, it has the power to either pull certain materials in, like iron, or push them away. And every single magnet has two ends, a north and a south pole. They follow a really simple rule: opposites attract and likes repel. So a north and a south pole will pull together, but two norths, they'll push each other apart. And this fundamental push and pull, well, that's the engine behind a ton of our technology. But what actually gives magnets this power? I mean, we can see the effects, but where does it come from? The answer, it turns out, is hidden deep down at the subatomic level, inside the atoms themselves. So it turns out an atom can generate its own tiny magnetic field. Physicists call this a magnetic moment, and it does it in three ways. You've got the electron's orbit, the electron spin, and the spin of the nucleus itself. But while all three play a part, one of them is way more powerful than the others. First up, you have the electron's orbit. Just think about it. As an electron zips around the nucleus, that moving charge is basically a tiny electric current, and any electric current creates a magnetic field. It's a neat effect for sure, but it's not the main show. It's not where the real power of magnetism comes from. No, the real powerhouse, the main event, is the electron's spin. Now, this is a fundamental property of the electron, just like its charge or its mass. It's just part of what it is. You can kind of picture it like a tiny, perpetually spinning top. And it's this spin that turns every single electron into its own little powerful magnet. This is the true origin of the magnetic force we see. Okay, so wait a minute. If every electron is a tiny magnet, then why isn't everything magnetic? Why can't I stick my coffee mug to the wall? Well, it all comes down to how all those tiny atomic magnets are arranged inside a material. So let's take a look at the different magnetic families. The brilliant scientist Michael Faraday, way back in 1845, was one of the first to really dig into this. He started sorting materials based on how they reacted to a magnetic field, and he came up with three main groups that, we still use today. Okay, so here's the breakdown. You have diamagnetic materials like water or gold. These are actually weakly repelled by magnets. Then you have paramagnetic materials like aluminum, which are weakly attracted. But the real superstars of the magnetic world are the ferromagnetic materials. We're talking iron, cobalt, and nickel. These guys are strongly attracted to magnets, and this is the crucial part: they can become powerful magnets themselves. All right, so let's zoom in on those ferromagnetic materials. How does a regular, boring lump of iron transform into a powerful, permanent magnet? Let's break it down. So, inside a normal, unmagnetized piece of iron, all those little electron spin magnets aren't just a total mess. They actually group themselves together into these little neighborhoods called domains. Think of each domain as its own tiny magnet. The problem is, all these tiny domain magnets are pointing in completely random directions. They're all working against each other, so their magnetic fields just cancel each other out. The net result? No magnetism. But then, we bring in an external magnetic field, and that field acts like a drill sergeant, shouting orders. All the domains that just so happen to be pointing in the right direction, they start to grow, gobbling up the domains that are pointing the wrong way. The whole material starts to get organized. And if you apply a strong enough field, all the domains line up and merge into one giant superdomain. The entire piece of iron is now aligned, all its tiny magnets pointing in the same direction. And bam, you've got a powerful saturated magnet. Okay, that's cool. But what happens when we turn off that external field? Do things just go back to being a random mess? Well, no. And this is where a really fascinating property called hysteresis comes in. You can think of it as magnetic memory. The material doesn't just snap back to how it was. It remembers being magnetized. This chart, the hysteresis loop, it perfectly illustrates this memory. See? Even when that external field drops back to zero, the material holds on to some of its magnetism. That leftover magnetism is called remnants. It's how much of that magnetic history it keeps. And to completely wipe that memory clean, you actually have to apply a magnetic field in the opposite direction. The amount of force you need to do that is called coercivity, basically how stubborn the magnet is, how hard it is to make it forget. So, this whole idea of magnetic memory, how much it remembers, and how hard it is to erase, this isn't just some neat physics trick. It's the absolute key to engineering pretty much all of our modern magnetic technology. Because by playing with this memory, we can create two totally different kinds of magnets. On one hand, you have soft magnets. They have very little memory, a really narrow hysteresis loop. They're super easy to magnetize and demagnetize. This makes them perfect for temporary jobs, like in electromagnets or generators. Then you have hard magnets. These guys have a powerful memory and a big, wide loop. They're tough to magnetize, but once you do, they hold on to that magnetism for dear life. And that makes them perfect for permanent magnets. And a perfect everyday example of hard magnets in action? Electric vehicles. Those powerful, super efficient motors that drive modern EVs, they rely on incredibly strong, permanent rare earth magnets to generate that constant magnetic field that keeps the wheels turning, mile after mile. But magnetic memory isn't just for making things spin. There's another absolutely revolutionary application called giant magnetoresistance, or GMR for short. Now, this is a mind-bending quantum effect where a super tiny magnetic field can cause a massive change in a material's electrical resistance, basically controlling the flow of electricity. And this little trick, it's the principle that underpins our entire digital world. So think about how we store data. A GMR sensor is built from these impossibly thin layers of magnetic and non-magnetic materials stacked like a sandwich. Now, if the magnetic layers have their spins pointing in the same direction, parallel, electrons can just zip right through. The resistance is low. We can call that a digital 1. But if the layers have their spins pointing in opposite directions, anti-parallel, the electrons get scattered all over the place. Resistance skyrockets and the current stops. And that's our digital 0. So this GMR technology lets a tiny magnetic head read those ones and zeros simply by detecting that huge change in resistance. It is, quite literally, what makes modern, high-capacity hard drives possible. I mean, this breakthrough was so huge, so world-changing, that the scientists who discovered it were awarded the Nobel Prize in Physics back in 2007. So think about that. We went from the invisible, quantum spin of a single electron all the way to electric cars in the very foundation of our digital world. It just goes to show you how understanding the absolute smallest things in the universe can lead to the biggest revolutions in technology. Which really only leaves one question, right? What's this fundamental force going to unlock for us next?